In this video, I'm going to illustrate a couple of visual approaches and statistical approaches for assessing your multiple regression results in SPSS for heteroskedastic errors. One of the assumptions of least squares regression is that you have homogeneity of error variances or homogeneity of residual variances. And when you violate that assumption and the errors exhibit heteroskedasticity, although the effects are not really will not be present concerning the actual unstandardized regression coefficients, there are effects on the standard errors for those coefficients. And this can lead to an increased likelihood of committing a type 1 or type 2 error when you're making inferences about the corresponding population parameters. So to illustrate this process of evaluating errors, basically we're going to start off by just running a least squares regression. So I'm going to go to Analyze, go to Regression, and to Linear. And I'm going to put my dependent variable, which happens to be achievement, and my independent variables into their respective boxes. So I have self-efficacy and ability as predictors of achievement. So so when I run the basic analysis, I basically get all the standard least squares results. You can see here's my R-square value, the f-test addressing the significance of that R-square value, as well as the unstandardized regression coefficients for each of my predictors and the standard errors. And then over here you have your t-tests, which are just basically formed, our t-statistics, which are basically formed by taking the ratio of a given unstandardized regression coefficient to its standard error. And then you have your p-values indicating statistical significance. Now, to evaluate for heteroskedastic errors, what we can adopt two different approaches. One is visual and the other one is more statistical. So we'll start off with the visual approach, and basically I'm just going to rerun this again. And in this case, I'm going to click on Save, and I'm going to ask for unstandardized predicted values, and then unstandardized and standardized residuals. I can also ask for studentized if I wanted to. Some of those other things are pretty common things to request, which helps in terms of assessing for outliers and things like that. But mainly we're going to be focusing on the issue of heteroskedastic errors in this particular video. So here we have the fitted y values, or the predicted values on y, or the predicted achievement scores as a function of the two predictors. We have the unstandardized residuals. Here you can see we have standardized residuals and even studentized residuals. So in terms of visual approaches, the first approach I'm going to illustrate is pretty basic. Basically, what we're going to do is go to Graphs, Legacy Dialogs, and then down to Scatter Plot. Click on Simple Scatter and then Define. And so the first thing we're going to do is we are going to create a scatter plot where we have along the x-axis the unstandardized predicted values from our least squares regression, and along the y-axis I'm just going to go ahead and use I'll just go with the unstandardized residuals. So we'll click on OK. And so now as you're looking at this visual right here, it should be kind of apparent. Basically what we're doing is we're looking at how the residuals are distributed around 0. And essentially, heteroskedastic errors are oftentimes illustrated or demonstrated where you have low, at certain values on your, in this case, the unstandardized predicted values or the fitted values, you have less variation evident in terms of the residuals, and then at other levels you have greater variation. So, if, just kind of visually, you can look at this plot right here, and you can see that in terms of the distribution of residual errors, it kind of looks like this. So it looks like that, as scores are increasing on in terms of the predicted values on y or the fitted values, you can see that the errors are exhibiting greater dispersion. So you can see less spread or dispersion at lower levels of your fitted y values and greater dispersion at higher levels. So at any rate, so visually that would suggest that we might have some evidence of heteroskedasticity. Basically, what we're looking for in terms of evidence of lack of heteroskedasticity, or basically what we call homoskedastic errors, is, if we had our predicted values, and just kind of pretend this is a straight line. If we had our predicted values, what we would see is a random display of points around 0, and or something kind of akin to this, and you would not see any kind of evidence of any greater spread or dispersion as scores increase in terms of the predicted values or the fitted values. So you could see that basically the errors would seem to kind of fall within these ranges right here, and would not exhibit this sort of fan-shaped pattern that we see over here. So at any rate, so we have some evidence of heteroskedastic errors just looking at the fitted values and their plots against the unstandardized residuals. So we might also want to look a little bit more closely at the individual predictors to see, is there a given predictor that exhibits more of a relationship with the unstandardized residuals than other predictors. So we could do this by predictor as well. So in this case, I'm going to take the unstandardized predicted value out, and I'm going to put self-efficacy in as a predictor. And so in this particular case right here, when we look at the dispersion of residuals, once again we see this fan-shaped pattern sort of emerge. So you can see that really at lower levels of self-efficacy, you see less dispersion, and then you see, particularly as you get way on up into the upper levels of or higher scores on self-efficacy, you see a greater dispersion. So you see a little bit more of a fan-shaped pattern there. So it looks like there might be some heteroskedastic errors as they relate to the self-efficacy variable. And then we can also do the same thing looking at the other variables. So we'll take self-efficacy out and we'll put ability in. And in this particular case, once again, you see sort of a similar general pattern here of dispersion of errors. So you can see that sort of, again, kind of a fan shape, maybe not quite as pronounced, but still kind of a fan shape appearance there. So visually there's some evidence of heteroskedastic errors. And another option visually is what we could do is we could actually, if we take those unstandardized residuals and square them, and we can run our plots again. So in this case, I just clicked on transform compute, and so I'm just going to create a new variable called residuals squared. So under the target variable, you just put whatever the new variable's name is going to be. So that's just what I chose. So now I see here's the unstandardized residuals, and what I'll just do, I can just put 2 asterisks right here and then a 2, and that is telling SPSS to square my residuals. So now I'm going to click on OK, and so now when I look at my data set, I have that variable has now been created. So now what I could do is I could basically do a similar sort of look at the data. So in this case, I'm just going to put the squared residuals on the y-axis, and I'll put my predicted values again on the x-axis. And so once again, you can see in this case, most of the residuals are down here in this little area. So you can kind of see down here in this area. Proportionally, but you also see that there's a fanning out as we get up into higher levels on the predicted values. So essentially we have this sort of fan-shaped pattern again, and here's the lowest residual you can have is 0. So there's our fan-shaped pattern here. So we can also do that by predictor as well. So you can see. We'll do graphs scatter plot again, simple scatter, And in this case, I'll just put self-efficacy on the x-axis. And once again, you can see that we have very pronounced fan-shaped pattern. So you can see that the residuals are clearly increasing as scores on self-efficacy are increasing. Then also, if we look again at our other variable, go to graphs again, for ability. Once more, we have this sort of fanning out. So really, there's pretty good evidence visually for heteroskedastic errors in our data set. So those are some visual approaches that you can take in order to assess for heteroskedastic errors. There's also statistical approaches that can be utilized. One approach that can be utilized is called the Breusch-Pagan test. And so the basic logic behind that test, and also the White's test, is very similar to what we have when it comes to using Levine's test in the context of analysis of variance, which is that we're testing to see if there is significant variation in the variances on our dependent variable across levels of the independent variable. So at any rate, with the Breusch-Pagan test, there are a couple of variants that I'm going to talk to you about. And basically, the first variant, basically these approaches involve what are called auxiliary regressions. So in other words, essentially what we'll be doing is regressing our squared residuals variable onto our predictors in various ways. So I'm going to go and create my first auxiliary regression by just hitting reset, and I'm going to take the squared residuals and put it in as my dependent variable, and then I'm going to put in the unstandardized predicted value or my fitted y values from the original least squares regression. So at this point, now when I click on OK, now I can see if there is a relationship between the fitted predicted values on y and the squared residuals. And you can see the r-squared value is 0.208, and we have a f value here, which indicates really that we have a significant relationship between the fitted values on y from our original least squares regression and the squared prediction errors. So right there, that is evidence that we have essentially evidence of heteroskedastic errors. Another variant on this is if we run this, and instead of using just the unstandardized predicted values, we could actually use the original predictors. So I'm going to put self-efficacy and ability in here as predictors and click on OK. And so now you can see that we have the r-squared value is 0.246, and you can see that the set of predictors accounted for significant variation in the squared residuals. So this is the f-test. Again, that's addressing the omnibus effects of the predictors on the dependent variables. So yes, there is a significant relationship between the predictors and the squared residuals. Moreover, we can come down here and we can actually look at the relationships between our predictors and the residuals. So we could actually assess for significance in terms of which of the predictors is significantly related to the residuals. So at any rate, these are two variants of the Breusch-Pagan test. There's also other variants as well that involve a chi-square test. This seems like this is probably the quickest and most efficient way of carrying out the test using SPSS. So one thing to note, though, is that because we're including just our original predictors in here. Really, all we're doing at this point is looking to see if there's a significant linear relationship between the predictors and the squared residuals. However, it's also possible that our variables could be related to the residuals in a nonlinear sense. And so that's one of the limitations of the Breusch-Pagan heteroskedasticity test. So another option is White's test, which basically is, for all intents and purposes, building on the Breusch-Pagan test. To do this, what we do is we essentially, we're going to leave our R-squared, our squared residuals variable in our data set. And in this case, what we do is we take each of the predictor variables and we square them. So we create squares of the predictor variables as well as a cross product term. So we'll start off by just creating a squared variable for self-efficacy. So we'll go under transform and compute variable. And like I said, this is en route to computing the White's test for heteroskedasticity. Oops. So I'm going to type in self-F, and then I'm just going to call it squared. And so I'll just say self-efficacy *** 2, and click on OK. And so now I have a new variable that's in my data set. I'm going to do the same thing for ability. So I'll just call it ability squared. Click on OK. And now what I'll do is I will create a cross product of those two variables. So now I'm going to call this, I'll just call this cross for lack of a better, more creative name for it. So I'll just say self-efficacy by ability. Okay, so now I have squared terms for my two predictors as well as the cross product term. Let me be clear on this that right now I'm just running a regression analysis that happens to have two predictor variables. The original two predictor variables was self-efficacy and ability. Let's say I had three predictor variables. Let's say I had self-efficacy, ability, and motivation. In that particular case, if I was running White's test, then I would be squaring self-efficacy, squaring ability, squaring motivation. I would then create cross-product terms for self-efficacy and ability, self-efficacy and motivation, and ability and motivation. So you can see that you can run into having a whole lot of variables that you're creating, the more predictor variables that are in your original model. So at any rate, now we're going to run our auxiliary regression, and so I'm going to click on Analyze, okay, Regression and Linear. And so I'm going to take these guys out. Well, actually, I should have left them in. So I'm going to leave these in, as well as the self-efficacy squared, ability squared, and cross product. So like I said, if I'd had a third variable, then we would be adding even more variables into this, and you can see it gets pretty clunky pretty fast. But at any rate, if I click on OK, you can see now that my R-squared value is 0.385, and you can see that our model is statistically significant. So in this particular case, we had 1, 2, 3, 4, 5 predictors in the model. And the overall prediction model predicting those squared residuals was statistically significant. So again, we have evidence of heteroskedastic errors. When we look at the individual regression coefficients and their significance tests, you can see that none of them were statistically significant, and it's probably because there's a fair amount of interrelationships among our variables. So one of the downsides of White's test, like I said, is that you can end up with a whole lot of predictors in the model, the more predictors that you had in the original least squares regression. So the effect of that can be that you end up losing those extra degrees of freedom from the error term, and so you actually decrease the likelihood of finding significance if there is if there are heteroskedastic errors. So another option or a way around this that I have observed is if you go to transform, compute variable, and in this case what we can do is we can basically take our unstandardized predicted values and square it and then model that as a predictor. So in other words, I'll just call this predicted squared. And so we'll just take our fitted values from our original least squares regression and square them. Click on OK, and so now we have our predictor, our variable here. And so now when we run our analysis, we'll use those, instead of using this entire set of predictors, what we can do is actually, I'm just going to reset this here, and I'll put our fitted values that are squared as a predictor of the squared residuals. And so then I can click on OK, and so now you can see that this test will suffice in that respect. So instead of having multiple, basically losing a lot of extra degrees of freedom from the residual term as a function of a large number of predictors, we only lose the one as a reflection of, or the one degree of freedom as a function of the predictor. So in this case right here, we can see that our squared fitted values from our original least squares regression was a significant predictor of the squared residuals. So that last procedure I took from Jeffrey Wooldridge's introductory econometrics text from 2009. So at any rate, this pretty much concludes my discussion of how to evaluate your least squares regression results for heteroskedastic errors. And I hope you find this useful in your own research.